Hello, my amazing students. This is Mrs. A, and I am back from my vacation. We had a great time. I think I got a little bit of a cold, but hey, when you got 13 grandbabies running around, you're bound to come home with something, and a cold's not too bad. We had a blast, and I am here to finish 8.3 as promised, which is the hypothesis testing for the mean of a population. So here we go. Okay, so we have done our basics of hypothesis testing in 8.1. That was actually broken up into two videos, a part A and a part B. And then our 8.2 was testing a claim about a proportion, and that turned out to be one 40-minute video, which is already posted. And the last thing that will be in chapter 8 is going to be testing a claim about a mean. We will start with the mean of a small sample, which has got n is less than 30, and the standard deviation is unknown, just like we did in 7.2. If you remember correctly, we're really following the same pattern we did in 7.2 for the proportion and the mean. So we're going to do that for chapter 9 as well. Chapter 7 and 8 and 9 are all flowing through proportion testing. A brief introduction of 7 was confidence intervals, and 8 is hypothesis testing. And then 9 is going to be hypothesis testing the difference between two means and stuff like that. So this is, we're going over and over the same type of a situation. We're going to talk about the proportion, which is a binomial situation, which we can treat as a normal situation because certain parameters are met. And then we test the claim about a mean, which we start with the standard deviation not known and a small sample size, and then we progress to being able to use the standard normal when we meet certain qualifications. So the 8.4 is not in the scope of this class. We skip that one entirely. All right, so here in the chapter 8.3, we are testing the claim about a population mean, and it is one of the most important methods presented in this book. We use this a lot. Part 1 of this section deals with a very realistic and commonly used case in which the population standard deviation is not known. Part 2 includes a brief discussion of the procedure used when the standard deviation of the population is known, which is very rare. So here are our objectives and our notations, which have been the same on each one of the slides. Oops, I need to move down just a little bit. There we go. So we get all the screen in there. All right, so then the requirements. So testing the mean when the sigma is not known, the standard deviation of the population is not known, is going to be the first probably 5/6 of this lesson. And then we only have a little bit of a time because this author really de-emphasizes the standard deviation being known because it occurs so rarely that you would know the standard deviation of the population and not the mean. So realistically, we don't really use those as much. So this is the case we're going to use over and over and over again. So about 5/6 of the lesson is going to be on sigma not known, and then just a small portion is going to be on sigma known. Okay, so here are the requirements. The sample is a simple random sample, and either or both of these conditions are satisfied. The population is normally distributed, or n is greater than 30. If one of those is not satisfied, we can't use our standard z-scores or our t-distribution. The t-distribution, remember, is only able to be used if the population is approximately normally distributed, or n is greater than 30. Okay, so here is our test statistic for the claim of a mean. We're going to use our t-distribution because we have not got our standard deviation available. So we're going to use our sample standard deviation. Our p-values, we're going to again use technology, or we're going to use the student t-distribution. Your p-value is going to be your percentage or your area in the tails that are beyond your critical value. And then we're going to have the different degrees of freedom, because remember, when we're doing small samples, sigma not known, we use the t-distribution, and the t-distribution has degrees of freedom, just like we did in 7.1 and 8.1 and 2. So, well, 8.2. So then critical values, we're going to use the student t-distribution to get the t-scores instead of the standard normal to get the z-scores. Okay, so here we have some more about requirements. Requirement of normality, or n is greater than 30. We cannot use the t-distribution or the z normal without these being met. Okay, so if the original population is not itself normally distributed, we use the condition n is greater than 30 for justifying use of the normal distribution. Sample sizes of 15 to 30 are sufficient if the population has a distribution that is not far from normal. In this text, we use the simplified criteria for n is greater than 30 as justification for treating the distribution of the sample means as a normal distribution, regardless of how far the distribution departs from the normal distribution. If the samples are large enough, samples tend to start to act normally. So that's going to be one of our justifications, is n is greater than 30. Okay, so, but remember, in this one right here, we're talking about sigma, or the population standard deviation, is not known, and that is our key for needing to use the t-distribution. All right, so here, find critical values in a t-distribution. Identify the level of significance, alpha, right? Remember, we can find our alpha from our problem. If we do not have that specified, we let 0.05 be our default alpha. Identify the degrees of freedom, which is going to be our number in our sample, takeaway 1. We're going to find the critical values using table 5 and the index B in the row n-1 degrees of freedom. If the hypothesis test is left-tailed, now how are we going to know that? We know this by our what? Our alternative hypothesis. If our alternative hypothesis is less than, we use a left-tailed. If our alternative hypothesis is greater than, we use a right-tailed, just like we did before. If we have a not equal to, we use a two-tailed. So, one tail alpha, one tail alpha. So, column with a negative sign, column with a positive sign, and two tails, we're going to have the negative and the positive sign. Now, what are you going to do if you approach a different t-table that does not have positive and negative signs? There are different tables that do not look the same as the one we have in our book. So you can supply the plus and minus signs because the area will be the same, and you're just supplying the plus and minus sign to say whether it's on the right or the left. So it's really not that complicated. So here's an example for finding the critical values. Find the critical value t sub 0 for a left-tailed test given alpha is 0.05 and n is 21. If n is 21, then our degrees of freedom will be 20. Okay, so there's our degrees of freedom. We're going to look at alpha is 0.05. Since we have a left-tailed test, we're going to look for one tail alpha column. Okay, and so we're looking on the left-hand side. When we go look at this, we get t is negative 1.725, and I'm going to show you that now in your book. Okay, so when you're looking over here, this is our table, t-table, in the back of our book, t-distribution, critical values. And they're showing you that when you have a left-tailed test, your critical t-value is going to be negative. So here, notice they don't have negative values. You are to supply the negative values, which is the way it is in most t-tables. Your right-tailed test has got, since it's right-tailed, our t-value will be positive. And then two-tailed, we're going to have a negative and a positive, but we have to split the alpha and put it into each tail. All right, so over here, we've got area in one tail, area in two tails. And let me hold my page still there. Now remember that over here, you can see the relationship. You've got all your alpha in one tail. And then over here, you've got all your alpha in one tail. And then over here, you've got half your alpha that is in each tail. So together, it makes one alpha, but you get a half an alpha in each tail. So now let's look at the relationships up here. The alpha is the area that is all together. So if all of the area is in one tail, that should be the area of the two tails together is the alpha. Okay, so area in two tails is the alpha. So if we have 0.05 in two tails, then we have 0.025 in one of the tails. So you can see the relationship there, that this one, the area in two tails, is double the area in one tail, because the two tails means the alpha is split in half. Okay, so let's look at the situation we were looking at here. We had our n was 21, so we're going down to degree of freedom of 20, and we're going across to a left-tailed test. So we're going to look up area in one tail, and we're going to look up an alpha of 0.05. So all of the alpha is in one tail. So we're going to look up one tail, 0.05. So there's our one tail, 0.05. All of our area, all of our alpha is in one tail right now. And we're going to go down to the 20 until we come across and we get 1.725. Okay, so we go back and we look at our slide, and you see down at the bottom, instead of 1.725, it's negative 1.725, because we have a left-tailed test, which means it is to the left of the mean, and the mean is 0. So instead of positive 1.725, it's negative 1.725. We're going to look down. The 0.10 was our alpha, and that is the area that's in two tails. But notice that half of that is going to be in one tail. So we're running down the same one here, and we're going to go all the way down to number 25, because we have a degree of freedom that's a little bit bigger now. So we're going to go all the way down to 25, which is that yellow line, 1.708. But remember, this is a two-tailed, so we're going to have a negative and a positive. And there we have down at the bottom your 1.708 and your negative 1.708, because you have two tails. So now here's our general cheat sheet on what we have to do a t-test. Now, I put the qualifications that are going to allow us to use the t-test up here. Population normal, small sample, n is less than 30, sigma unknown. This allows us to use a t-test. If we had a small sample and sigma was unknown, but we did not have population normal, then we would have to, we would not be able to use either test. State the claim mathematically and verbally. Identify the null and alternative hypotheses. Test statistic is the sample mean. So state our H sub O and H sub A. Specify the level of significance. which is usually given to you. Identify your alpha. Identify the degrees of freedom. Degrees of freedom is n-1. Determine the critical values. We're going to do that from our T-chart. Determine the rejection regions. Okay, so go to the next screen, and we have our test statistic, our standardized test statistic. We want to always sketch our sampling distribution. We want to make a decision to reject or fail to reject the null hypothesis. This is very similar to what we just finished doing with proportions in the last section. Okay, interpret the decision in the context of the original claim. So now we have important properties of the student T distribution. These were also listed for you in the 7.2 when we first introduced the student T. So this is a slide that I put it in both PowerPoints, so you have seen this one before. The student T distribution is different for different sample sizes. The student T distribution has the same general bell shape as the standard normal distribution. Its wider shape reflects the greater variability that is expected when S is the sample mean is used to estimate the sigma. And the student T distribution has a mean of T is 0, just like our normal distribution, but the standard deviation of the student T is greater than 1. And as the sample size n gets larger, the student T distribution gets closer and closer to the standard normal distribution. So here we have an example. A used car dealer says that the mean price of a 2008 Honda CR-V is at least $20,500. You suspect this claim is incorrect, and you find that a random sample of 14 similar vehicles has a mean price of $19,850 and a standard deviation of 1,084. Is there enough evidence to reject the dealer's claim at alpha is 0.05? Okay, so this is adapted from the Blue Book. Okay, so here's our little framework for our hypothesis testing, and let's go through each one of the steps. I'm hoping that you're beginning to see that this is not as complicated as many people make it out to be. Stating your H sub O and H sub A, the claim is that the mean is at least 20,500. The alternative will be the less than, because the equal situation always has to go with our H sub naught. Our alpha is 0.05. They gave that to us. Our degree of freedom is 13 because our sample size was 14. We're going to take our alpha, and since this is left-tailed, always look at your alternative hypothesis. It's moving to the left, so we have a left-tailed test. That means our whole alpha goes in the left. So we're looking for alpha 0.05 in one tail. And when we go to our chart, we're going to see that. Okay, so 0.05 in one tail is the one we want to look at. Okay, and we're going to follow it all the way down to our degree of freedom of 13, which is this yellow line right here. So we're going to get 1.771, and this is in a left-tailed test, so we should make that 1.771 negative. Okay, can you see the negative 1.771 here? Let me see if I can get a little bit closer and grab that. Okay, so you can see the negative 1.771 down here. That is my T sub 0. That is my critical value, my reference value right there. Now I'm going to go over here, and I'm going to calculate the test statistic that goes with the sample mean minus the projected mean, the mean of the claim,
And now we're taking our data and plugging it in. We're getting our test statistic for comparison to this T sub 0, which is our critical value. It is the one that we cannot go back past if we want to stay in the reasonable area. Anything over here is very abnormal and causes us to reject our H sub O. So here, because our negative 2.244, which is our calculated t-score, is actually in that blue tail. That blue tail is called your rejection region. Since it's in the rejection region, we will reject our H sub O. At the 5% level of significance, there is enough evidence to reject the claim that the mean price of a 2008 Honda CR-V is at least $20,500. So you're going to be able to check these and decide for yourself whether you're getting a good car deal or not. And if you can show the salesman that, hey, the price really is not $20,500, and I can show you statistically, you might be able to get your car for $1,000 cheaper.
Now, wouldn't that be cool?
Okay, notice we're still testing the mu with a small sample. That means we're still using a t-distribution. An industrial company claims that the mean pH level of the water in a nearby river is 6.8. You randomly select 19 water samples and you measure the pH of each. The sample mean and the standard deviation are 6.7 and 0.24 respectively. Is there enough evidence to reject the company's claim at an alpha of 0.05? Assume the population is normally distributed. So this is going to be the claimed mean, and then so we're going to assume that is the mean of the population. This one was the mean of our sample, and we're going to subtract the two. And then we're going to have to put this into our equation for our sampling error as shown here. All right, so 6.8 is the claimed mean. The claim is that it equals 6.8, so the H sub A will be that it does not equal 6.8. So anytime we use a does not for alternative hypothesis, we're automatically going to a two-tailed test. So our alpha is 0.05, our degree of freedom, 19 minus 1 is 18. Our rejection region is going to be in two tails, and since we have 0.05, we're going to split that into two tails and do the math there, and then we're going to get our critical value, which is going to end up being negative 2.101 and positive 2.101. We're going to get that from our table by looking up the 0.05 in two tails. So let's do that. Okay, so here's our 0.05 in two tails. We're going to follow that down to degree of freedom 18. And we get 2.101. Since it's in two tails, we're going to use plus and minus 2.101. As you can see down here on our screen, then we calculate our test statistic. The data that we are given, that we're having to say, okay, this is our situation. This over here applies to every situation where you have a two-tailed test at a 0.05. Okay, so, but remember that this degree of freedom changes with each problem and gives you a slightly different value. So now, because our negative 1.816 is going to be in the middle and not in the tails, we're going to fail to reject the H sub O. At the 5% level of significance, there is not enough evidence to reject the claim that the mean pH is 6.8. Okay, so here we have another example. The author obtained times of sleep for randomly selected adult subjects included in the National Health and Nutrition Examination Study, and those times hours are listed below. Here are the unrounded statistics for this sample. N is 12. X bar is 6.833333. S is 1.9 blah blah blah. Okay. A common recommendation is that adults should sleep between 7 hours and 9 hours each night. Use the p-value method with a 0.05 significance level to test the claim that the mean amount of sleep for adults is less than 7 hours. Okay, so let's go to checking our requirements. Remember, this one came out of your textbook, so it's a little bit different format. We have a simple random sample, and we have a normally distributed population, and N is greater than 30, so we've met those requirements. The sample size is N is 12, so that does not exceed 30, so we're going to use the t-distribution. Okay, so here, the accompanying histogram and the normal quantile plot, along with the apparent absence of outliers, indicate that the sample appears to be from a population with a distribution that is approximately normal, so both requirements are satisfied. So basically, what they're saying is they did not say that the population is normally distributed. So we had to look at the distribution. Okay, they just told us that they never made that statement that it was approximately normally distributed. So we had to go over here and kind of look at a histogram to see if it looked like it was generally normally distributed. Okay, so they're saying it is. I won't give you anything nebulous like that on the test, so don't get too worried about that. All right, so here we have the claim that the mean amount of adult sleep is less than 7 hours becomes mu is less than 7 hours. That's going to become our H sub A, because what we need is an equal sign or a greater than or less than with an equal sign for H sub O. So this one is going to become our H sub A, and then we write our H sub O. So basically, the alternative to the original claim is mu is greater than or equal to 7. This is going to become our H sub O, and this one is our H sub A. Okay, so here they have them written here. So the mean, and this one is a typo here. We have the claim is less than. This one right here should be greater than or equal to, and I've noticed several typos when I take the book slides over. So that one should be greater than or equal to, and it should be the same thing as right there, but for some reason it doesn't show up there, and I'm not sure why. Step 4 is to specify the level of significance, which is always going to be 0.05 if they don't state it, but this one was stated in the problem. Because the claim is made about the population mean, the sample statistic is going to be X bar. We will use the t-distribution because we are not qualified to use the standard normal. We're not qualified to use the standard normal because we do not know our population mean. Okay, so we're going to have to use our S instead of our sigma in our problem, and that's what makes it a t-distribution, is the absence of that sigma. So when we get done calculating, we get negative 0.290. Now this is our standardized test statistic. This is the one we're going to compare, but we don't have the critical value that goes with this. So what we're going to do is we're going to go to our technology, okay, and we're going to plug in. Here's our TI-83. We're going to go to a t-test. We're going to plug in mu is less than 7, because that, remember, is what we're testing here. We're going to say mu is less than 7, and then we're going to say the p, we don't know that yet. They're going to give that back to us. We do know our X bar, and we do know our sample standard deviation, and we do know our N. So let's go do a t-test. I'm going to show you how to do that very quickly on your calculator. Okay, so hit your stat button and go over here to test.
Right, so we're going to go down one to the t-test, and we're going to hit enter. Right, so now if you are using the data itself, then you're going to have it on the left, the data. But we're using the stats. They provided us with the stats. Our mean that they gave us was 7, and our X bar was 6.8333333, a whole bunch of threes. And S of X was our sample standard deviation, which I entered from the problem. Our N was 12, and we're going to have less than the mean, and then we're going to hit calculate. So let me come down here. Everything looks right. We're going to come down here to calculate, and we're going to hit enter. And then I get a screen very, very similar to what they have. There is the TI-83, TI-84 part of the PowerPoint. The only thing is that it's very interesting to me is that the last digit is different on mine. Of course, it's so far out there that it doesn't matter much. But if you look at the two of them together, let's see if I can, you can see that the last digit is off on both the t-score, the critical value, and the p-value, which is interesting to me. I don't know why that happens, but it's so far out there it really doesn't matter. Everything else is the same, and that is a t-test. So notice that your t-test gives you the p-value. The p-value 0.3887, because we're going to round it to 4 decimal places. And when we look up at our screen, the p-value here is 0.3887. The thing we need to note is that our t-value does not have percentage values like our standard normal table does. We have to go to technology to get the p-value. Look at your t-chart with me. T-chart only has alphas and t-scores and degrees of freedom. There are no other areas on a t-chart. If you are asked to find a p-value, which is an area, which is a percentage of the curve, you're going to need to go to technology, and I suggest that you zoom in on that TI-8384, which is a t-test. We have that p-value. The p-value is greater than the level of significance, which is 0.05. 0.38 is much bigger than 0.05. So since the p-value is larger than the alpha, that means it's not in the tail, which is the rejection region. Therefore, we fail to reject the null hypothesis. And it says because we fail to reject the null hypothesis, we conclude that there is not sufficient evidence to support the claim that the mean amount of adult sleep is less than 7 hours. All right, so here is another one using p-values with t-test. So again, we're going to have to go to the calculator and get that. Department of Motor Vehicles office claims that the mean wait time is less than 14 minutes. So our mean mu will be less than 14, will be our h sub a, and our h sub o would be greater than or equal to 14. A random sample of 10 people has a mean wait time of 13 minutes with a standard deviation of 3.5 minutes. And now our sigma is 0.10. Test the office's claim. So now we're going to get our little skeleton of our hypothesis test, and they're going straight to here. The one that we can use is a t-test. We're doing it from the stats, not the individual data. We have our mean that they're suggesting, 14. Our x bar is 13. We got all of this from the data, and then we're going to calculate it.
and they put the answer on there. So the p-value that comes back in the calculation is 0.1949. Now this one is a less than, so it's a left-tailed test. And we had 0.10 in one tail. And the p-value is greater than that, which means it's not in the tail, which means we will fail to reject H sub O. There you have it. And the p-value method without technology. If suitable technology is not available, we can use table A3 to identify a range of values containing the p-value. Okay, in using table A3, keep in mind that it is designed for positive values of t and the right tail areas only, but left tail areas correspond to the same t values with negative signs. So let's go look at table A3. Okay, so this is basically going through that process of trying to use a t-table to make a decision when you don't have technology available. I would not even mess with it because you're going to hopefully have your calculator when you come to take a test. And so basically they're saying that when you look at the negative 0.290, you can't find the area, but you can see that examine the values of t in the row for the degree of freedom 11, which was what this problem was, to see that 0.290 is less than all of the listed t values in the row, which indicates that the area in the left tail below the test statistic of negative 0.290 is greater than 0.10. Okay, so to me, I'm going, you should have your calculator. I'm going to allow you to use a calculator instead of do this kind of guessy method. So I wouldn't even worry about this slide. I would just, when you have to find a p-value, you make sure you have your calculator so that you can do it using your technology. I'm not going to make you find a p-value without it. Okay, so here we go. The critical value method. So critical values we can do without the technology because our t-chart gives us the critical values that go with a certain situation. So it says left tail test, and they gave us the test statistic, which is negative 0.290. The sample size n is 12, so the degree of freedom is 11. Okay, so given the significance level of alpha in 0.05, refer to the row. So since it's left-tailed, we have a 0.05. We're going to go all the way down 0.05 in the left tail and go to 11 degrees. So let's do that. So when I go to 0.05 in one tail and I go all the way down to degrees of freedom 11 right there, I get 1.796. Since this is a left tail test, it's going to be negative 1.796.